Good evening. My name's Lori McCollum, and I'm here from Progressive Action for the Common Good, the Environmental Forum. I don't know if you've heard of our group, but it's been in existence for about 13 years. We advocate a lot of progressive issues. If you're interested in learning more, we have some information at the back. We have 3 forums that meet regularly. One is on healthcare, one is on civil rights, and then our forum is on the environment, and we meet once a month on Mondays, the first Monday of the month at, is it 6:30? Or 6:30 at Cobblestone Place in Davenport. And if you want any more information, you can sure catch me afterward, but my email is on those little green flyers, all of our emails, for those of us who are chairs of the forum if you need any other information. But thank you for joining us tonight on this beautiful evening. And I'm honored to welcome Ray Wolf, who is the Science and Operations Officer for the NOAA National Weather Service in Davenport. He's responsible for managing operations, staff training, and local research. Prior to arriving in Davenport in 1994, Ray was a forecaster at the National Weather Service office in Denver, where he evaluated new forecast and warning science technologies that formed the basis of the NWS modernization. He also served as an agricultural forecaster in the Mid-South, supporting farmers and producers in the region with weather and climate information. Ray received a master's in agricultural climatology in 1985 and a bachelor's in meteorology in 1982 from Iowa State University. So I'd like to welcome this evening Ray Wolf. I've heard his presentation, it's very interesting.
Thanks, folks, for taking time out to come here tonight. I really appreciate the opportunity to share the science of climate change with you. And I'll acknowledge my able assistant, Susan, who's going to be flipping the slides for me. If we could go to the next one, please. What I want to talk about tonight isn't my opinion. It's the consensus of the entire climatological community. 97% on a survey agree with the information that I'm presenting tonight. It stems from the IPCC report and also the recently released Climate Science Special Report. That's part 1 of a 2-part report. The second part will be issued later this year. It's part of the National Climate Assessment, which is a congressionally mandated requirement to put these reports together every 4 years to look at the state of the science and the climate and where we are across the U.S. One of the neat things in working in this area is that it's connected me to some of my former professors at Iowa State who are engaged in that, and also at the University of Illinois. So whichever side of the river you live on, your land-grant university is contributing to this research. Next, please. So, and I do want to stress that climate change is a science issue. The climate has always changed, but the issue today is that the change is occurring at such a tremendous pace, and that change is caused largely by human factors. What to do about climate change, and it seems to be the focus of many of the activities of your group here, is a policy issue or political issue. I'm going to stay away from policy and politics and stick just to the science, because policy is not my area of expertise by any means. Next, please. So the graphic up here shows the greenhouse effect, and this is the fundamental issue we're facing. If you think about the energy from the sun and how it interacts with the earth, it's akin to your checking account where you have income and spending. And the key, of course, to the checking account is to keep the two in balance. And when they're in balance, life is good. In yellow is energy coming from the sun. Now, if you remember back to elementary school science class about the electromagnetic spectrum, the energy coming from the sun is called shortwave radiation. And when it impinges on the Earth, several things can happen to it. It can hit the atmosphere and bounce back into space. Some of it does. It can hit clouds and bounce back into space. But most of it comes down to the Earth. A little bit is reflected back by the Earth's surface, and then it's absorbed at the Earth. And then it transitions into what we see at orange, into long wave radiation. And this is akin, if you go out on a day like today and stand in the sun, you're feeling that shortwave radiation come in and you're warming up. You are experiencing this transition from the shortwave radiation to the long wave radiation. And the long wave radiation can go through several pathways. It'll warm up the Earth's surface and the ocean. A good deal of it will go back out into space. Some of it will be reflected back down to the Earth by clouds and also by greenhouse gases. And again, as long as things are in balance, we're in good shape. But when you add greenhouse gases, and I'm speaking particularly carbon dioxide, methane, and nitrous oxide, you're increasing essentially the thermal blanket to the atmosphere, so less heat is getting out into space, and we are no longer balanced. We're accumulating heat at the Earth's surface. Next, please. To put this in a little bit of history to give perspective to the issue, the idea of the greenhouse effect was first pushed back in 1861 by John Tyndall. So this isn't the greenhouse concept, it is nothing new, well over 100 and some odd years old. It was later, in the latter part of the 19th century, that Arrhenius pointed out that what humans were doing would add to the greenhouse gas. So what are we talking, 1896, 124 years ago. So a warming climate is not a new idea. It's existed for well over a century. Now, in 1983, I actually attended my first scientific conference at the University of Illinois that talked about climate trends. And there were several scientists at that time already engaged in looking at this issue, and there were concerns and expectations that continual additions to greenhouse gases would warm the globe. Then if we zoom ahead to 2017, a lot of the material I mentioned is coming from the first part of the National Climate Assessment. Next, please. I mentioned the three greenhouse gases, the primary ones, carbon dioxide, methane, and nitrous oxide. And you see a graph there starting at 1850 on the left, going all the way across to near the current year on the right. And the vertical axis is the amount of energy that amount of gas can keep from escaping out to space. So we see with the red curve the big increase in carbon dioxide, the effect that carbon dioxide has on the atmosphere, followed by methane and several other CFC type gases, and then nitrous oxide. Interestingly, although methane is not the biggest contributor on a molecular level, it's actually the most efficient thermal insulator to the atmosphere. Next, please. And if we look at these, I apologize, the graph probably looks a little bit noisy in the back of the room, but this data goes back 800,000 years ago. It represents at the top the amount of carbon dioxide, and then methane, and then the nitrous oxide back in time. And you might wonder, how do they get this data back 800,000 years? Well, if you go to like the Greenland ice sheet or to the Antarctic and you take ice cores, as you go down vertically, it's like going back in time. Similar to geology, if you've ever been out west or in parts of the eastern U.S. where they've done road cuts through mountains, and you see the layers, the strata of rock. In the same way, snow piles up over time and gets deeper and deeper. We all know, much like ice cubes, when ice cubes freeze in our freezer, they trap air bubbles. And whatever is in the air, whatever constituents are in the air at the time, is what gets trapped. So you can take these ice cores and go back in time, can melt them, and quantitatively assess the chemicals that are in the air, And from that, you can plot these graphs. And we see, especially with carbon dioxide, notice a little periodicity, kind of an up and down change over time. And that's kind of the natural climate change we talk about. And that has to do with a slight wobble that the Earth axis has over geologic time, on the order of 50 to 100,000 years. And we see as the Earth tilts a little bit closer to the sun, it warms up and you get more vegetation and hence more carbon dioxide. But I want to call your attention to where the graph is today. And if you look at those values in each one of them, in the upper right-hand corner, the amount of carbon dioxide and methane and nitrous oxides we're seeing in the atmosphere today far outstrips anything we've seen in the last 800,000 years. And that's really the crux of the issue, is that we have taken something that's imbalanced and we have thrown it out of balance. And the contribution to the chemicals in the atmosphere have come from us. Next, please. So we have this graphic. This actually makes for a nice poster. You might see it a few sites around town, or I've passed them out. The 10 indicators of a warming world. It's not just looking at data, but we can go look at the physical parts of the world and the biological parts of the world too, and see what's going on. So if we take a look at sea surface temperatures, and in that case we're talking about the upper tens of meters of water temperature, they're warmer today than they were 100 years ago. If you look at the overall ocean heat content, that's from the top surface all the way down to the deepest parts of the ocean, the overall heat content has gone up. In fact, much of the excess heat that we've generated since greenhouse gas burning started in the industrial age has gone into warming the oceans. Sea level has increased as a result. The air temperature over land has increased. The air temperature over sea has increased. In the lower part of the atmosphere, the layer of the atmosphere between near the surface and where you see jets fly, where you see the contrails outside, has warmed. We've seen decrease in aerial coverage of snow this year, notwithstanding. We're actually one of the few parts of the northern hemisphere that are colder than normal this month. Most of the rest of the hemisphere is warmer than normal. Glacier melting is increasing, and humidity in the atmosphere. And I'll ask folks who are my age or thereabouts, if you grew up in the Midwest, don't summers seem more humid today than what they used to? And we're finding we're running our air conditioner more than we used to, actually to deal with the humidity more than the increase in heat. Next. So if we look at this at a global perspective, on the left is a plot going back to the late 1800s and using the 20th century average temperature. So we see early in the period we're below that 20th century average, and we see the graph indicates that over time we've gone above that average and continue to go above that average to the tune of nearly a couple of degrees Fahrenheit. But the warming is not exactly equal over the globe. There are parts of the globe that are warming faster than other parts. The Arctic area in particular and Antarctic are some of the fastest warming areas. And as we'll see shortly, the southeast part of the U.S. is not warming nearly as fast as some of the other areas. Next, please. This is another way to display data. And if you look at the top, you see January. And if you go clockwise around the circle, see February, March, May, so on, all the way around to December and back to January. And then what the scientists did is plot each month's global average temperature over time and then connect the dots. So he starts back in the 1800s, and you see the temperature in the 1850s in purple. And as time goes on, you see the circles are getting bigger. That represents the increase in temperature globally until you get to where we are today. So this is just kind of a different way, I think a more exciting and interesting way to view the data than just a simple bar graph. Next, please. So the question frequently comes up, well, how do we know that man is responsible, that humans are responsible for the increase in warming? That's one of the benefits of the computer models we use both for weather forecasting and climate forecasting is it allows you to experiment a little bit. And we see the climate models plotted on the left there with the actual temperature, global temperature in black. And we see that the climate models actually simulate the past pretty well. And that's a routine part of the scientific process is when they develop a new computer model is you go back and look and see how good does that computer model do at simulating the past, where we know what the outcome is. Well, all of our climate models, and in fact the weather models that we use on a day-to-day basis include greenhouse gases. So as a thought experiment, you could rerun those models and take out the greenhouse gases and see what happens. And that's shown in the graph at right, specifically the dark blue line. And what we see is if you take the greenhouse gases out, the model predicts the temperature to hold pretty steady through the century and into the first part of the 21st century. And we know that's not the case. So deductively, the difference between those two graphs is due to greenhouse gases. Next, please. And another way to look at this, there are other things that certainly influence our climate. We see the greenhouse gases in the graph at top, and I apologize, the exact values aren't critical for this, but graphically we see in red is the solar cycle, and we see with the sunspots, the 11-year cycle, and you see a lot of periodicity that every 11 to 22 years, amplitude higher and then lower. But if you look at the trend over time, there's really no difference in the trend from the sun over time. Yes, it changes from decade to decade, but it's not getting warmer. The next graph in blue is volcanoes. And volcanoes are kind of an interesting aspect of climate. The big volcanoes, especially those in the tropic, that explode and get a lot of particulate matter and sulfur chemicals up into the stratosphere that is above the level jets fly, those are the ones that impact climate. But when they do, that impact, which is cooling, only lasts for a year or two. So volcano impact is very transient and not at all long term. And after the particulate matter and whatnot descend into the lower part of the atmosphere, things return to normal. The green line there is natural variability. This is what I want to show is that if you think of climate change in terms of trend, what the long-term trend is, an upward line over time, we still have that year-to-year variability. So winters in this century have been the warmest of the last 100+ years. But this winter has actually been just normal compared to the prior two winters we've experienced, which were well above normal. So we still have that year-to-year variability as we're all kind of riding uphill with the warming climate. And the bottom graphic there in blue shows a contribution from the greenhouse gases and the rapid increase over the last century especially. A different way to look at it is the bar chart at right, which gives you a relative feel for the impact on the climate that each of those things have. The human-caused greenhouse component is the red bar chart. The solar there in the middle is the orange bar chart, and volcanoes are the green. So you could see the scale at which our contribution to climate is impactful is well beyond anything we're seeing from the sun. Next, please. So I'll ask, what have we seen around here? And this is great, especially talking to farmers in the longer growing season. We've seen wetter springs, more humid summers. I talked about humidity. milder winters, and the more variable and extreme weather and floods as well. I think especially if you've been around as long as I have, how maybe some of these things have changed over time and how things today are not like what they used to be. Next, please. So if we take a look at temperatures across the U.S., this is looking at basically the last 30 years compared to the first half of the 20th century. We see areas in red have warmed over that time. The annual graph is the large one on top over most of the U.S. So the brighter red is the greater warmth. Not so much in the southeast part of the U.S., but over the country as a whole, definitely so. Now, if you look at that in terms of winter versus summer, you see actually much of the country, much of that warmth is coming in the winter time, which probably folks up here aren't too disappointed by that. If you look in the summer, though, it's kind of interesting. If you head out west over the summer, and especially up north as well, we do see the warming signal. In the center part of the country, the warming signal is more muted, and we believe that's because of the increase in humidity in the atmosphere. Our humidity source is the Gulf of Mexico. The rains, the heavy rains we get in the summertime come from the Gulf of Mexico, as it does all over the central part of the U.S. So we think the increased moisture is negating a part of the warm-up, especially during the daytime. Next, please. So if we look over Iowa, and I picked Iowa because that's where I'm at, but the graph looks just about exactly the same for Illinois. That blue line shows the trend in temperature for the entire year, the average yearly temperature trend over time. But we see we still have that year-to-year variability shown by the purple line. So the climate change signal is really kind of subtle in terms of how we think of things day to day. But again, if you do comparisons to, when we were kids 50, 60 years ago, the change becomes more dramatic, and you can see why we're looking at the blue line there. Next, please. And I mentioned the summertime. We look at the temperatures on top. That's the average daily temperature in the summer in Iowa, and there's a very slight increase, not very strong signal at all. But when you look at the nighttime temperatures on the bottom left versus the daytime temperatures on the bottom right, things get more interesting. We see our daytime temperatures during the summer are not necessarily as hot as they used to be, but our nighttime temperatures during the summer are. And this is a result of the increase in humidity, the humidity helping keep the temperatures up during the nighttime, and also being a factor, among other things, in our increased use of air conditioning and increases in precipitation as well. Next, please. And for winter, we see the same kind of graphs there. The blue line in top, the overall winter temperature is warming over time. And if we look at the nighttime in the winter versus the daytime, they're both warming, but nights in winter are warming faster than daytime in winter. Next, please. So the question becomes, we've pretty well documented that we're warming, our temperatures are warming. The observed record shows it in our part of the world, and in fact over the globe. So the question becomes, where are we going to be for the rest of the century? And the first thing the scientists will ask, well, how much carbon are we as a society going to decide to burn over the rest of the century? And so in order to provide some guidance to policymakers, what we can do with our climate models is assume different levels of carbon dioxide. We can assume that we're really aggressive at reducing greenhouse gas emissions. Or we can assume that we're going to continue on as we do, or we can run cases for in between. And then we see what the potential outcomes are for each of those. So the difference between acting aggressively and not acting at all can kind of be quantified and give policymakers a sense of what the potential impacts are. And we do that, we refer to them as different scenarios. And in the graph at the right, we see the actual temperature in black. And then we see three colored lines, green at the bottom, blue in the middle, and red at the top. Those are three different scenarios. The green is the aggressive scenario. The blue is probably a more realistic scenario. And the red is a business as usual. And you see for our part of the world, depending on what we do by the end of the century, we'll see another 2 to 8 degrees of warming, depending on how that falls out. Now, something I should mention, you notice this graph is in Fahrenheit, and most of the graphs and whatnot I'm showed is in Fahrenheit because that's what we're used to here. But if you get online and looking at some of the climate change literature, you might see some of the graphs and tables they use are in centigrade. So be careful of that because the Fahrenheit is a more finely resolved unit than centigrade is. So the numbers won't look the same, but they'll obviously all be in the warming direction. Next, please. So if we look at scenarios, we have these maps, a mid-century scenario on top and a late 21st century scenario on the bottom, low emissions on the left and higher emissions on the right. And the warmer the color is the increase in temperature in Fahrenheit based on which scenario, which pathway we go down, and what part of the century you're looking at. But some of the commonalities you see is the Arctic is warming, continues to warm at a greater rate than the rest of the U.S. And depending on where we're at, by the end of the century, somewhere on the order of 4 to 6 degrees at the low end, and perhaps 8 to 10 degrees on the higher end by the end of the century. So it's important, again, when you're looking at this in the literature or reading stories in the newspaper, see when they're talking about these projections, are they talking about the middle part of the century or the end of the century, and then what emissions scenario are they assuming? Because they have fairly significant effects on the actual outcome. Next, please. So locally, this says Iowa, goes for Illinois too. Regional models, you see the past record in orange there, and then the low emissions is in green, and the red emission, or the higher emissions is in red. And you can see for our part of the world the types of outcomes that are being expected at this point. Next, please. But it's not just temperature that's affected, it's also precipitation. On these maps, the areas that are greener are wetter, and areas that are in the tan or brown colors are drier. This is the same thing, the last 30 years compared to the first half of the last century. And we see, so across the U.S., much of the central part of the U.S. and the Northeast is on the wetter side. We see dryness maybe more so, especially in the Southwest, out in the western part of the U.S. On the bottom, we see winter, spring, summer, and then fall, and we see variations out there. Wetter springs for much of the upper Midwest and actually good portions of the Corn Belt we've observed already. Summer precipitation has been toward the wetter side. On the fall, it's kind of interesting. Our area is in between this sort of drier wedge with wetter to the northwest and wetter to the southeast. So again, the overall trend for us is wetter, but the seasonality is different. And this is a big deal. How this plays out is a big deal for agriculture and ag production. It's also a big deal out on the West Coast. You see the western states, drier winters. Snowfall in the mountains out west provides their reservoir of water to get through the rest of the year. And if we've seen this year with them running behind normal in parts of the area, that's a huge amount of water. This isn't something where you could build a few reservoirs and store what you need to get through. The amount of water the mountain snowpack provides out west just entirely dwarfs what's being retained in man-made reservoirs. So serious issues out west. Of course, California is one of our major agricultural producing states too for specialty crops. So there are implications for that too. Next, please. And if we look at Iowa or Illinois precipitation over the last century, these are 5-year blocks. The lighter green are below normal, and the darker green are above the 20th century norm. And we've seen that in the last couple of decades, that trend toward wet is showing itself in this data as well. Next, please. But again, distribution is everything. This is the same graph except for spring. Wet during the spring is problematic. It's when our soils around here are bare and most subject to erosion. It's when farmers are trying to plant to get a crop in. So there's some serious implications for that increased frequency of wetness. Next, please. For this graph, I want to draw your attention to the upper right, which basically shows increase in frequency of heavy precipitation amounts. And that is, if you take the real high end of heavy rainfall events and just look at how those have changed all the time, what we're seeing is a substantial increase. I think that's a 42% increase in our area in heavy precip events. The issue there is these extreme rainfall events challenge our infrastructure, our sewer and drainage. They're problematic for farmers because after about the first inch or so that runs into the soil, much of the rest of the heavy rain runs off and is of little use to agriculture, and in fact can add to the increasing erosion issue, which leads to water quality issues as well. So both a water volume, a water quantity issue, and a water quality issue with the heavier precipitation. Next, please. And we see that this is a number of 2-inch or more rainfall events at a particular site. We see a lot of the lighter green in the early part of the last century, below the 20th century average, and increasing numbers over the last 30 years or thereabouts. Next, please. So in the future, looking down the line, this is by season for high emissions scenarios only, because high emissions scenarios are the ones that are probably most problematic for us. We see the Arctic areas actually get wetter over time, as we've seen already. And in winter and spring, we're in the wetter area, the green as well. But what's a bit disconcerting is in the summertime, we look much of the U.S. in the summer turns drier. And if you think of the agricultural production and it's dependent on rainwater especially, there is a lot of irrigation out on the plains, but there are limitations to how that can evolve over the future. This lack of summer rain could be problematic from an agricultural production standpoint as well. Next, please. So, and if we look in the future then at increases in heavy amounts of precipitation, we see for both the lower emissions scenario at the top and the higher emissions scenario, there's an expectation of an increase in the frequency of heavy rainfall events, more so for the higher emissions scenario and less so for the lower emissions scenario. So you see, depending on which scenario or which pathway we take in our future greenhouse gas emissions, it can have a pretty significant effect on what the final outcomes are. Next, please. Snow cover, maybe after this year, nobody's going to be too bothered by this graph, but over the latter part of the last half of the century, our snow cover, that's aerial coverage in the springtime, has been on the decrease. Next, please. So I mentioned we've had all this warming going on. It begs the question is, where has the warming gone so far? How is it partitioned out between different parts of the planet? And the oceans have basically absorbed by far the bulk of the heat, followed next by the atmosphere, the continents, the actual land surface, and then the energy that's gone into melting various aspects of our ice domains, the glaciers, Arctic, Antarctic, and the Greenland ice sheets. There's some thought that the ocean is reaching a point where it's sort of maximized in its ability to absorb significant amounts of heat, which means that heat's going to have to get partitioned elsewhere, and the obvious remaining one is the atmosphere. Next. So sea level rise is an interesting issue that comes with multifaceted impacts. The biggest part of sea level rise has come simply from the fact that the ocean is warmer, and we all know as things warm, they expand. And the bottom of the ocean is fixed, so the sea level has to get higher. There's some contribution from the Greenland ice sheet, from Antarctica, and the glaciers too. You notice the Arctic is not on there. The Arctic ice sheet floats on the water. So when it melts, the ice that displaces the water is replaced by the meltwater. So the Arctic ice sheet melting is kind of a net zero type situation. So next, please. So the future projections of sea level, again, depend on what we do with our carbon budget. You see various scenarios, anywhere from a couple of feet to as high as 8 feet. And of course, that's disconcerting, considering that we've got a percentage of 5% of our population lives within 4 feet of sea level. And if you think of all the major cities on the coasts that are near sea level, if you're a farmer or know anybody who farms or is involved in any way with exporting goods to other countries through seaports, rising sea levels don't bode well for seaports and that infrastructure. And also, from a fiscal standpoint, you can imagine the resources it'll take to remediate the coastal areas, or even in some scenarios to evacuate and repopulate elsewhere in some cases. There are a lot of implication for future monetary outlays that can be extrapolated from that graph, depending on which scenario we end up going to. Next, please. This graphic at the Arctic shows the Arctic in 1984 at top. You can see in the white the aerial coverage at ice, and then in recent years where we're at roughly today. And the graph at the bottom, the blue, shows the trend line in decreasing Arctic coverage. This has had a pretty fascinating impact on the Arctic from a physical standpoint, but also a biological and a cultural standpoint. Next, please. And I'll speak more of that shortly. Extreme events. I think most of us are familiar with the bell-shaped curve in the upper left. That's basically a measure of temperature distributions, whether you look at it over monthly or annual time frames. And we see the tails in blue and red, the blue on the colder side and red on the warmer side. It's kind of your infrequent type events. What's expected to happen in the future, and we've seen already, is basically that entire bell-shaped curve gets shifted to the right toward the warmer end of the spectrum, so that high record temperatures, warm record temperatures occur with a much greater frequency than cold record temperatures used to. The same thing happens for precipitation, which is the bottom two graphs. Precipitation is not a normal distribution, so the graph looks different. But again, as we're shifting toward a wetter climate, and a wetter climate with more heavy precipitation events, we're taking away from those lighter precipitation events, and that's what the graph shows on the right there. So our extremes are changing as well. Next, please. This plot shows the relative ratio of warm and cold record temperatures. Where you see a blue bar for a year, that means we had more cold record temperatures that year. Where you see a red bar, that indicates we've had more warm record temperatures that year. And we see, especially since 1990, far and away the warm records are dominating over time. Not every single year. We still have that variability. I think that tall blue line there was 2014, a couple of years ago, when we had a pretty chilly winter even around here. Next, please. So extreme weather, certainly one of our concerns from a weather service perspective is, what does this mean in terms of severe weather events? We know that heavy rain and flooding is on the increase already. We've seen, and last year may have been an example, an increase of the strength and number of Category 4 and 5 hurricanes. Now, that doesn't necessarily imply that all those hurricanes will hit land, or even that the increase in frequency will tie directly to an increase in landfalling hurricanes. It's just the actual number of hurricanes both in the Atlantic and the Pacific. But one of the fascinating aspects of our science is how it impacts and interacts with society. And if you think about even here locally, if you go back, I moved here in 1994, I think Elmore and 53rd and that whole area, that was just farmland. There's no retail development there whatsoever. But now we see this big extension in retail area, new housing developments. So if you think about the Quad Cities, our footprint, our urbanized footprint has increased in aerial coverage. So without climate change, the odds of a tornado causing damage in the Quad Cities has gone up just by virtue of our bigger urbanized footprint. Now you put climate change on top of that, and you could see a doubling to that increase because the climate is changing, and that's superimposed over a society that's becoming more vulnerable to weather and climate extremes. Next, please. I mentioned Alaska. I was up there for a conference a year ago, and it's very sobering. Concerns about permafrost melting and how that might alter the carbon cycle, but also methane. Methane, a lot of frozen methane in the permafrost up there. Of course, they're seeing a reduction in glaciers, in ice sheets, and reduction in seasonal snow cover, which leads to an increased wildfire risk for them. Because, of course, as long as we have snow on the ground, that holds the wildfires at bay. There's some thought, and this is research that's ongoing as we speak, that changes in the Arctic might influence our weather patterns down here. So there's concern for how that might play out. And then I mentioned the cultural impacts. The native societies up there have grown in sync with the environment, and now the environment is changing at a faster rate than they can adapt. That polar bear picture there is not because it's the sort of cutesy pie, poster child for climate change. When polar bears are forced on land because of lack of sea ice, that increases in human encounters, which will typically end poorly for one or both involved. And there are people today who are deceased because of polar bear encounters that occurred because sea ice wasn't present, which would have been their normal habitat. So there's some real life and death and important cultural aspects to this, even beyond the physical and biological sciences. Next, please. I could go on for another hour on these topics. I'm sure you'll appreciate that I don't. But for agriculture, and I speak so much about agriculture because it's a big deal here. I mean, we're in the hometown of John Deere. What goes on in agriculture in our states impacts what goes on around the world. So the concerns on the agriculture side, an increase in growing season, which can be viewed as a positive in some respects, certainly from the plant. There are concerns about, with this changing rainfall distribution, about increase in drought potential. As the temperatures warm, the types of insects, diseases, and weeds we'll see are more characteristic of what we see south of here. So we might see introductions of pests that farmers in the south are dealing with that we have to deal with too. And that variability of precipitation, the timing of precipitation, for example, for corn is so critical to final yields that changes in that can be problematic. Energy. This drought several years ago in Texas really brought to light the linkage between energy production and drought. You think about all your power plants, including Cordova, right up the river here, are on rivers and use that water for cooling. Well, what happens if that water is not available or not available in sufficient supplies? And what happened a couple years ago at Cordova, when we get into drought, of course, the river levels go down, the water temperature in the rivers go up. So Cordova didn't have as much water to draw on. The water they were bringing in is warmer than normal, and we're running our air conditioners more, so they have a need to generate more power. So they get into this catch-22. They actually had to get a waiver from the DNR to be able to return the water to the river at a warmer temperature than they had been permitted to. The DNR manages that so as to minimize the impact on the ecosystem, but they had to get a waiver. Of course, on the ecology side, a lot of folks, if there was something I could wave a magic wand and have school kids taught, it would be ecosystem services. Kids hardly know where their food comes from today. They surely know little, broadly speaking, about where their clean water and clean air comes from. And I don't mean from Iowa American water or your tap in your bathroom. I mean, where does it come from an ecosystem standpoint? As the climate changes, it stresses these systems that are responsible for providing us these services. On the human health side, heat stress is the obvious thing we're concerned about. There are also impacts to other diseases as it interacts with various insects that we might not be used to seeing, or as the growing season is longer, you can get multiple generations of insects. Or in some cases, as winter is cooler, we had reports in Scott County at the end of last winter of a significant increase in tick population because we had 2 warm winters back to back, and the cold weather didn't kill off the ticks like what we're used to. Hopefully this winter has helped some in that regard. Business and political side, business-wise, there are already companies making climate change planning. Political issues notwithstanding, if you're a company that wants to be in business, large corporations, especially down the line, and you are sensitive to various aspects of the climate, you're certainly making contingency plans for different things in your long-term planning. And politically, that paper was talking earlier, water drought, climate change, and conflict in Syria. This issue in Syria had a significant component related to drought, which impacted their food supply, which was at the same time corn prices went up so high here. So you had this menagerie of different impacts happening that drive food prices up, cause societal stress, actually across the area of North Africa. And there's a significant component to the political goings-on that we see today. There's also the Sahel is expanding southward at almost a pace you could measure on a yearly basis, and that's resulting in populations immigrating primarily to Europe. So it's not just political or terrorism that's chasing migrants to Europe. There's also a strong climate signal to what's going on there too. Next, please. So this graphic kind of nicely depicts where we might be. We looked at the lower emissions scenario. Illinois is in the gold color. The higher emissions scenario, Illinois is in the red. See the mid-century are the two northern indicators, and the southern is the end of century. Now, Lori mentioned I spent some time in Mississippi, in west central Mississippi. We don't want that climate here. That was really miserable during the summer down there. It was not fun for outdoor activities at all. The mosquitoes were a 24/7 issue. Ticks were really bad outdoors. It's just not a fire ants and all sorts of nasty things down there. So I think that gives kind of a nice picture that summarizes what we've talked about for the last hour here. Next. And everything that you've seen can be traced back to this or similar references. I'll point out the www.climate.gov website is a wealth of information. That includes this report, the first part of the National Climate Assessment, and my email's up there too if you have any questions. And with that, if you have any questions here, I'd be glad to take them. Thank you.
The first one is when you were putting the slides up on projections for the future on the different factors, temperature, precipitation, sea level rise, you mentioned that some of the actions that could be taken to veer from business as usual are related to a carbon budget, maybe seaport export upgrades of some sort, or planning for that. But what are some other things that go into those changes to get us away from business as usual? And are those government regs and enforcement, or are those consumer driven?
And this is where we very quickly delve into the policy side, or can. But from a science perspective, certainly our energy production, none of this is a political statement, but transitioning from coal and natural gas to solar and wind balances that more in our favor. The economy is driving the transition from coal to natural gas, not the carbon usage. There was some study done by my parent agency that indicated if we had a national grid network that was direct current, which is feasible, that there's actually enough solar and wind energy across the United States to provide virtually all of our energy supply, and that could be done by 2030. Now, of course, that requires quite an investment, but the science is not a stretch. It's there already. So
That actually kind of leads into my second question, which was the data presented, how confident are you in the actual science behind the data? In other words, what are the strengths and weaknesses of the methodologies of the data and instruments used? And what would increase your confidence in the science going forward? And that's one answer.
well, it's certainly, our models are pretty good, but they're certainly not perfect, and there are aspects of them that they continue to work on to make them better. It's a continuing process. But the biggest source of variability is what we as a society are going to do. And the error bar in the model output, is this much, and the error bar in what society is going to do is like this. So if we could get a better idea of what society is going to do, and it's unforeseen things, like the economic downturn in 2008 globally had an obvious effect on greenhouse gas production because of that, the reduced reductions in the economic trade.
What was the grid, what do you call it?
It's a direct current. Folks maybe my age or older, my grandparents certainly remember the direct current. That gets into your science history with Edison and Tesla and those fellows. Direct current, there's a danger to it, and we're alternating current because it's relatively safer, but it's much less efficient. With direct current, you could create solar power in Arizona and ship it to New York pretty efficiently. Or you could create wind power in Iowa and ship it down to New Orleans and do it pretty efficiently. So, but there's transportation is a significant component of the carbon production. Just home energy usage. The transition to LEDs has been a good step. Eating beef, and I know I'm in farm country, so, but I just saw a statistic that 40% of the beef eaters account for 80% of the carbon production or methane production by livestock. So I'm not advocating everybody become vegan, and insofar as I'm getting into policy, which I probably should. They're talk to your doctor. There are health issues there too.
And Ray, when someone asks a question, could you repeat it? So I'm not sure people are.
Sure.
Yeah, and just my last question, I've already talked about too, but it was just, regarding the input on a local environment, I appreciate and wondered just how we as ordinary citizens in the Midwest can affect the larger national as well as global study. Kind of alluded to some of that as well.
So the question was, how can we act locally to have a global impact? And I'll kind of turn that around to the group. Let's say get together, and you're the perfect group to have this conversation. And it gets in the policy, which is away from my expertise, but you're the people to have that and be the leaders in the community. We talked about the Butte and some of the neat things going on up there. It can be done at the community level. You see in Chicago, the green roofs. A couple of years ago, I was at a conference and got a tour of the roof of the City Hall, the City Municipal Building. There's a green roof. I saw more prairie species out there than I do anywhere in the fields around Scott County. It was amazing. A lot of practical things. There's an air quality thing there. There's a water retention. You've cooled the roof, so the cooling aspect to the building in the summer and the heating aspect in the winter is reduced. There are all sorts. You see the Davenport Police Department has done it. So there are all sorts of ideas out there, and people are trying them. I'd look to some of the other communities around the U.S. and see what they're doing.
The warming of the Arctic what impact is that having on the jet streams and causing it to buckle?
The question is, what impact does the warming of the Arctic have on the jet stream? And that's an excellent question, and there are a number of researchers looking at it right now. And there's some thought, and this has gone through the peer-reviewed literature, but isn't at a point where I say it's broadly accepted yet, is because it's still being researched. But that some of these colder winters that we've seen and Europe have seen have to do with how the jet stream loops, because the ice, the changing ice, changes where cold air is produced in the Arctic. Because cold air, if you notice, in the wintertime when we have snow on the ground, the nighttime temperature is a lot colder than it is when we don't have snow on the ground. And we did a local study in our office. That's actually 10 to 15 degrees per night. So whether you have snow or ice cover is a significant local effect. And then if you put that on the scale of the Arctic Ocean, it becomes a significant regional effect and can, we think, impact weather.
You briefly mentioned something new that Dubuque is doing, but I was out of the loop, and I'm curious what that is.
The question is what's going on in Dubuque. I know the sustainability stuff. What I've seen is mostly related to water management and water quality and trying to manage flood runoff and rainfall runoff, a lot of stream flow restoration, and as they're doing that, they're improving kind of their green belt infrastructure and bike paths and such. But I'm sure there are other things going on, but that's what I'm most familiar with.
You said that a direct current system poses a danger. What danger is
The amperage coming through it will, if you've ever stuck your finger in a plug, the question was, what's the danger to direct current? And if you've ever got zotted by an AC current, like a cord that was frayed, you're still here to tell about it. If it was direct current, you probably wouldn't be here to tell about it.
Yeah, your data, your information, your graphic data is very impressive about supporting climate change and the urgency of what's happening with it. But it's making me think, along with our tremendous population explosion, we've predicted, 10 billion people by 2050, and a tremendous amount of increasing affluence, the need for energy, and the diminishing resources of clean air and food, especially. Do you have feelings or thoughts about this concept of whether we can get ourselves out of this mess by conservation, changing our lifestyles, versus technology will be an answer to us and we'll be able to always provide enough food and clean water for whatever the population?
The question is, with the growing population, can we manage our way out of the situation through conservation, or what kind of ways can we? That's a great question that I'm entirely not skilled to answer. That's really kind of a social science, it's a systems question. That'd be great for if we had a panel discussion up here with some social scientists and physical scientists, because there are lots of angles to your question, and a lot of it depends on what sorts of technologies come down the line. Cheap energy seems to be a solution for a lot of things, so I would think if we could figure that out. You're starting to see in cities old warehouses being repurposed essentially as indoor growth chambers for a lot of greens and things that restaurants use, since the locally grown food source is such a big deal. So if energy is cheap, that becomes very feasible to do on a large scale. I am a master gardener, so I'm semi-skilled in that area.
The recurring theme seems to be that there's 3% of the scientists that are holding out on the consensus. What's it going to take to get from 97 to 99%?
The question is, what about that 3% of scientists who don't agree? I could give you the snarky answer or the realistic answer. The realistic answer is I'm entirely amazed that it's at 97%, and I'm not going to worry about the 3%. Because we're at that point in the history of this science and research that we pretty well know what we know and know what we don't know. So the odds of that one random person having sort of the Darwinian perspective that changes the whole science on its face is not at all likely. So, good question, though.
I'm unsure exactly what is happening in the Great Lakes, but what threat is being posed by the melting of the ocean?
Well, with the Great Lakes, the biggest concern with the warming temperatures is increased evaporation over the course of the year, which would tend to lower lake levels. And I also know from talking to friends out west, they keep eyeing the Great Lakes and a big pipeline flowing from them to the west, which I think will never happen because the lakes are managed jointly by the U.S. and Canada. But they are a tremendous resource. Of course, there are a lot of things. Part of my parent agency's NOAA's background is oceans and Great Lakes. We actually have a research lab in Ann Arbor, Michigan that focuses just on Great Lakes issues. And of course, we have invasive things like the mussels, which are problematic. But some of the things that are more locally grown and tied to climate change are the algal blooms in Lake Erie, occurring from runoff from land. High nutrient runoff causes poison algae blooms in the lake, which makes them pretty much unusable for recreational purposes and can impact the ecosystem there too. So,
Well, it's very exciting to have this many questions. We have another one?
Just wanted to touch on your statement about the direct current issue. So since direct current may pose a greater threat than people are willing to deal with, do you think that electric utility companies might consider repurposing themselves in the future, and perhaps they could become servicers and maintainers of home generation systems, solar panels on roofs, personal property windmills, that kind of thing?
the question is, can today's power companies repurpose themselves to become basically supporters and providers of home-generated energy? Well, that's a great question that I'm totally unskilled to
If
answer.
that could like support a national grid for your
Yeah.
answering questions, I'm sorry, just curious.
So no, it's a good, I think thinking about things in a different manner like that is how you find a solution. I mean, somebody thought up the idea of a national direct current grid. And this would be like at the primary transport level, not down to our house. Kind of still be alternating current in our house. But they did a study and they used the climate models and looked at sun and wind and found that it's feasible.
One last one.
Hi.
This is it.
Obviously, when you were asking earlier what we can do locally, we really have to vote. We really have to vote. Every little teeny tiny supervisor, school board, they all will affect climate change. And deregulating certainly is happening. So I just am saying vote, please.
We have a little voter registration table back there. I'm guessing most of you are already registered voters, but certainly, you must strong arm your children and neighbors and get everything out.
That's right.
I would also encourage everyone to join some of the environmental groups in town. There's more than our forum. There's the Sierra Club. Mike, stand up. You're a leader in the Sierra Club. And there's other people. Catherine, you're a member, active member of the Sierra Club. Those of the members of the environmental forum, you guys want to stand up? I want to thank you for everything you've done and helped today. Come on, guys. Shirley's the only one. Mr. Wolf, for coming and talking to us. We have a lovely parting gift for you. This is an amazing bag
you can take with you to the grocery store, and it has our name on it.
I will use it too.
And I really want to thank everyone for coming out. We have lots of food left, help yourself. And anybody who's interested in coming to our next meeting, which is coming up what day is that? The 1st of May or whatever the first Monday of May is, 6:30 at Cobblestone Place. We would love to have like so many people we couldn't even fit you in the room. So we need to have a lot more people taking action in the Quad Cities. To me, it's kind of sad that we're being outshone by Dubuque and Cedar Rapids and Iowa City, who are already doing all kinds of things with sustainability, and we're not. Although I have to say, Davenport is a 4-star city, and they got that going when they put their roof on the police station, and they've done a lot of great things there. But there hasn't been a lot going on lately. We really need to increase that. Yes.
You know, the big table discussions that you've been hearing about in the media are going on tomorrow and Saturday. Sign up, go online, big table, Quad Cities big table. This is an opportunity to say, this is what we like our communities to be like and to become like. So take advantage. There's 500 of them.
Yes, there's 500 of those open tables, and if you haven't signed up, it's not too late. Also, you know, the main thing that gets communities more sustainable is something called the Sustainability Coordinator. Those are people whose jobs are to actually help coordinate and set policy and get things moving. The cities who have those kinds of things going have assigned municipal positions like that. And if you wanted to make that known to your representatives, your aldermen, your mayors, your city planners, that you would really like to see that happen around here, they'd be much more interested in getting that going. Because as we've talked to people, we get a lot of, you know, but we really haven't gotten anybody saying they'd be willing to make that sort of investment in this community. And since it's got 5, really, communities in the Quad Cities, it would make sense to me that something like that could be coordinated amongst us through something like bi-state regional planning. I mean, there's ways to make that happen and be financially feasible. But there has to be the political impetus from citizens to make things like that happen. So thank you again so much for your interest.
Thank you.